Okay, so the last thing that we're going to do is work through some practical application of this unitary transformation on the P.A Hamiltonian that we've been dealing with. Okay, and so now this is a really simple embodiment of the P.A Hamiltonian for the matter subsystem modeled as a harmonic oscillator. So I have, for my molecule, right, I've got a matter momentum operator in purple, p hat. I've got the mass associated with that molecule, m. I've got the charge associated with it, z. And then I've also got this 1/2 m omega sub m squared, x hat squared. So, right, this is the picture that we have for this is like I've got a cavity. It's got some cavity mode, right, for which I can draw the electric field and the vector potential with some direction pointed along these red arrows. And then I've got my actual molecule. I'm going to draw that in purple. So like CO, for example, right? And sitting in the cavity, right? And so then the dipole moment associated with that molecule points in the same direction as the field, right? And so this M would be the reduced mass. M is equal to mass of carbon times mass of oxygen over sum of mass carbon plus mass oxygen. And then the Z is basically, so we'll call this mu. That's the total dipole moment, and Z would basically be equal to mu over REQ, equilibrium bond length, and that sort of thing, right? So this is that model that we've been sort of dealing with so far, that I'm going to treat the vibrational motion of carbon monoxide within the harmonic approximation. So for that molecule, I've got a harmonic oscillator Hamiltonian, and then I'm coupling it to a single mode in the cavity, which has a vector potential associated with it, A hat, that's in red, and then I have the basically harmonic oscillator states of the photon, which I've written right now is 1/2 p sub c squared, p hat sub c squared for the photon operator for the cavity mode, plus 1/2 omega c squared, so that's the cavity frequency squared, times x hat sub c squared, so that's the position operator for the photon. Okay, so I've tried here to write all of my matter terms in purple and my photon terms in red. Okay, so now what I'm going to do is I'm going to apply this transformation shown here. So this is the so-called PZW transformation. And so importantly, this transformation is going to act on matter operators, and photon operators. And the reason why is because we have this exponential, this unitary operator is defined as an exponential of a product of a matter operator with a photon operator. So the matter operator is mu hat operator, that's the dipole operator. We can also, if we want, we can write mu hat as the charge z times the position operator for the matter, x hat. And a hat, just a reminder, the vector potential operator we'll write in this way. So square root of h bar over 2 times omega, that's the cavity frequency, times the permittivity in the cavity, epsilon naught. So I'm assuming it's, besides carbon monoxide, just a vacuum in the cavity. And then the cavity volume V, that whole thing multiplied by B dagger plus B. But also, you might recall A hat is proportional to the position operator for the photon. So another way I can write this is lambda naught times x hat sub c, where x hat sub c is the position operator for the photon. And lambda naught is this magnitude, which I've defined as square root of 1 over epsilon naught v. And if you're doubting that relationship, please go back and to your notes and look for the expression of x hat and p hat for photons in terms of b daggers of b's, because you will see that this relationship should hold up. Okay, so then as I've done that, right, like one of the things that I can see is A hat and mu hat, those are the operators in PZW, they're both position operators, right? So one is a position operator for the matter multiplied by some stuff, and the other is the position operator for the photon multiplied by some stuff. Okay, and so that's actually going to be really important. So it's going to be really important for what is the action of this transformation on the operator. And so one of the things that I'm going to argue for you right now is that I can do the following. I can basically say that tablet's frozen. There we go. Unfrozen. Great. So unitary transformations or sorry, let me say unitary operators with position operators will shift momentum, and similarly, unitary operators with momentum will shift position. Okay, so remember, right, I made this statement that I can always write a unitary operator as an exponential of I times a Hermitian operator, okay? So what I'm going to do in this case is I'm going to do one other thing. I'm going to just do this I over h bar. So that h bar is going to be important in this case because I'm going to now have a momentum operator multiplied. Actually, let me do this. I over h bar. I'll just have a magnitude, which I'm just for sake of notation, I'm going to call P naught multiplied by P hat. And I'm going to write another operator okay, and so this operator over here, you know what? Bad. So in both cases, P naught, let's make P naught and X naught unitless. And so if that's the case, then I'm going to have P hat over H bar. No, I really got to think about my dimensions here. So P hat is h bar over length. Okay, so then P naught has to have dimensions of length. Okay, and x hat is just length. And so, yeah, I still want to have h bar over here. And we'll have x naught should be h bar over length. Okay, great. And so, awesome. All right. So now P naught is going to be, a quantity which has dimensions of length. X naught is going to be a quantity which has dimensions of h bar over length, and that's another way of saying has dimensions of momentum, right? So what will result from each of these operators is that this operator, e to the I, h bar, p naught, p hat, is going to shift the position of my system by the amount p naught, right? And that is now a sensible thing to say because p naught is a length quantity, so it is something that position can be shifted by. All right. Now, same thing if I look at e to the I over h bar x naught, x hat, that's going to shift momentum by x naught. Okay, so the thing that you might critique me on, and I'm going to take that critique because I got my thoughts kind of jumbled up here, is that P naught is a really bad label for a position shift, and X naught is a really bad label for a momentum shift. I probably should have switched these. If I had switched them, if I'd been thinking more carefully, right, this is how I would have written them. Where I'm going to apply this position shift to shift position by x naught. And here I'm going to apply a momentum shift to shift by p naught. Okay. And so, but the real thing that I wanted, and here I got to keep fixing my labels. Okay, great. Now my labels are all fixed. I think that all makes sense. Okay, but the real important thing here, right, is that these unitary transformations are written in terms of a Hermitian operator multiplied by I and some magnitudes, right? And the operator that shifts the position, right, involves the momentum operator, and the operator that shifts momentum involves the position operator, right? So this is an interesting example where the conjugate operator, the operator is shifting its conjugate, basically. Okay, so now that is it took me longer than I wanted it to take to get to the point I wanted to make. My PZW transformation involves basically two different position operators, the position operator for the matter and the position operator for the photon. So what is it going to shift? I'm going to write a few choices, and I actually want you all to think about this. PZW operator. A, matter position and photon position. B, matter momentum and photon position. C, matter position and photon momentum. That was choice C. D is matter momentum and photon momentum. Well, let's check it out. What's our rule? Our unitary operators involving the momentum operator will shift the position. The unitary operators involving the position operator will shift the momentum. So if my PZW as a unitary operator contains a matter position operator and a matter momentum operator, a matter position operator and a photon position operator, then it will shift the matter momentum and the photon momentum. So the correct choice is D. All right. So hopefully you believe that just based on the rules, but let's actually apply it, okay? I mean, let's actually see why it's the case. So how do we actually take, how do we actually do these computations, okay? So what we're gonna say, right, remember, we have this relationship that the transformation of our operator. So here what I'm going to do is I'm going to write h hat prime, that's our transformed operator, is equal to u hat multiplied, or acting on our original operator, which I'll write h hat p dot a, multiplied by u dagger. Okay, so now this, because of the definition of u and u dagger as these exponentials of imaginary units times Hermitian operators, which is another way of saying, I probably should have been saying this all along, which means if I take the imaginary unit times a Hermitian operator, I get a different kind of operator called an anti-Hermitian operator. So there's always a way to write these u's, right, in the following way. E to, now I'm going to write b hat, where b hat is an anti-Hermitian operator, times h hat p dot a e to the minus b hat operator. Right? Because the adjoint of an anti-Hermitian operator is equal to the negative of that operator. Okay, so this is a strange kind of product which has this famous expansion called the Baker-Campbell-Hausdorff expansion, or BCH expansion. And so what we have is we're going to take that product and write it in the following way. So first term, so there's a whole expansion, right? And the first term is just the operator sandwiched in this product. So P dot A. Okay. Second term is the commutator of our anti-Hermitian operator, B hat, with the thing being transformed, P dot A. Third term is this crazy nested commutator. So I've got a commutator of the anti-Hermitian operator B hat with the result of the commutator of B hat and P dot A. Okay, and this goes on forever. It goes on forever. but that's okay. We're actually going to find out that we don't need to compute every term. This expansion is going to have a nice truncation, which is exact. So we'll see how that works. So now, how do we define B? Well, let's come back and look at P dot A, our PZW transformation. Okay, so I am going to take a look at this guy right here, right? So let's actually go ahead and copy this. So the answer to what is B hat, right? How I actually choose to write B hat is going to depend on which term I am considering. Okay, so what do I mean by that? Well, I have this P dot A Hamiltonian, and it has a whole bunch of terms in it, right? And so let's actually go ahead and copy the P dot A Hamiltonian again. And what I'm actually going to do is I'm going to consider doing the transformation of each one of these terms individually. Okay, and so as I do that, basically I can kind of make some arguments along the way that are going to simplify my work. Okay, so the first thing that I'm going to do, right, is I am going to say, all right, let's first consider acting on this first term here. So I'm going to call this whole thing term one. I'm going to call this whole thing term two. And I'll call this thing term three. And I'm going to call this whole thing term four. Okay. So then, well, what does that mean then in terms of how I should think about this expansion? Well, let's make a little room for expansion of PZW on term one. And what I want to really emphasize here, okay, term one may look like a complicated term to start with, right? Because term one has matter operators and photon operators, and the PZW is both a transformation for matter operators and photon operators. The important thing is, though, right, is that the PZW has the matter and photon position operators in it, right? Mu hat and A hat are fundamentally position operators. And this term one only has the conjugate of one of those, right? It has P hat for the matter. So it has the conjugate operator for the matter term only. And so the PZW is actually not going to operate on A hat. And the reason why it's not going to operate on A hat is right, like if I think about this expansion, I would really encourage you all to try this out, right? Pretend that you don't believe me. Try out these commutators where you're doing A hat from the transformation. So this B hat term contains the vector potential for the photon, and then this other term in the commutator contains A hat again, right? Well, A hat should commute with itself. And so basically all of the terms where you're trying to transform the A hat operator in the P dot A Hamiltonian with the A hat operator from your PZW, right, go to zero. All right, so just try that on your own. Now, here's what we're going to do now is we're going to write this transformation on term one in the following way. So I'm going to have U hat multiplied by 1 over 2m p hat minus z a hat squared u dagger. Okay. And so one of the things actually that we can do, right, is you may say, okay, I have to square this thing. Well, but actually what this has to be equal to is the square of the transformed piece, right? So this has to be equal to u hat right? And the reason why that's the case is because this is the identity. Okay. So, in other words, what I can do is I can actually take uh, the transformation on just p hat minus z a hat. And square that result and that's the same thing as this. Okay, right? Because what this left-hand side here, right, is identical. Oops, except for I have this stupid factor of 1 over 2m. I'm really sorry, everybody. Let's do the following here. Factor of 1 over 2m is just a constant. It can always go outside of this operator. Really sorry about that. That thing is not squared. This is the nice thing about the tablet. So I can clean all this up kind of more quickly. Okay, great. So now this term, this is identical, right, by definition to this term. the two green underlined terms are equal by definition. And but by realizing that mu dagger mu, u hat dagger u hat is the identity, then it becomes equal to this piece right here. Okay, so in this particular case, what I want to argue to you is that this transformation on just p hat is going to be a little bit simpler for us to see, so that's what I'm going to focus on. Okay, so let's do it. We've got essentially, if you recall our definition, copy this once more. All right, so what I want to do is say that, let's kind of rename my operator E to, so what we want to do is make this thing look like B, B hat. So now we'll have where B hat is equal to minus I over H bar Z A hat. And then I'm going to use my purple notation, my purple color for X hat, right? Because that's the one thing which is like an operator that I need to worry about as I transform this matter momentum operator. So I need to consider the X hat operator for matter. Okay, so that's what B hat is. All right, and so now what I can do is I can just take this piece here. I'm going to keep the mass out for now. And I'm going to write, now this thing is equal to the thing that I'm trying to transform, which is P minus Z A hat. Plus, now I need the first commutator, so B okay. And so let's figure out what this commutator is, okay? So what do I have in B hat? So let's just copy this in a new line. And let's expand B hat. Well, first of all, let's expand the commutator, right? So this is equal to B hat upon P minus ZA minus P minus ZA upon B hat. Okay, and now let's go ahead and expand B hat in terms of these operators. All right, and so this will be equal to, in the first B hat, I'm going to write minus I over H bar Z A hat. And then I've got X hat, P hat, minus Z A hat. Let me give myself a little room here. Okay. So that's the first term minus p hat minus z a hat, close parentheses. I've got a minus I over h bar, so let me go ahead and factor out that -1 here, times I over h bar. Actually, I'm not going to do that. What am I going to do? Yeah, forget about it. So just make this clear. This is a minus I over h bar z a hat x hat. Okay. So we can factor out of both of these terms, right? I've got a common factor of minus I over h bar z a hat. Okay, so let me factor that out. And then I'm going to have open parentheses, x hat, p hat, minus z a hat, minus p hat, minus z a hat, x hat. All right. And so what I'll now do is I'm going to distribute the x hat to both of these terms. All right, so now within these parentheses, I've got x hat, p hat, minus z x hat, a hat, minus p hat, x hat, plus z x, oops, x hat, a hat. Okay, so now I just want to really quickly remark that I have not worried about the order of x hat and a hat. And that's because x hat is our matter operator for position, and a hat is our photon operator. So they act on different spaces, so they can commute. So with that, right, this term exactly cancels this term. And what I'm left with is I over h bar z a hat multiplied by x hat p hat minus p hat x hat. Whoops, I need a minus sign there. That's important. Okay. And this is also the same thing as minus I over h bar z a hat multiplied by the commutator of x hat and p hat. So if you don't remember, the commutator of x hat and p hat is equal to I h bar. So this whole thing is equal to minus I over h bar z a hat, which I'm going to start writing in red again, multiplied by I h bar. Okay, so now what do I get? As a result, this h bar cancels this h bar. When I multiply this I with this minus I, I'm going to get plus 1. So this whole thing is going to be equal to plus z, oops, z a hat. Okay, with the plus sign, make sure that's plus. Okay. So now the other thing to note, right, I have, this is the result of this first commutator. All right. And so what do I know then? Well, first of all, the first commutator got rid of all of the matter operators, right? Now I only have the charge, which is not an operator, and I have a hat, which is a photon operator. And if I look further down my BCH expansion, right, the next term is going to be another commutator with b hat and the result of the first commutator. So if I have gotten rid of all of the matter operators through the first commutator, then the first nested commutator is going to go to 0. And then all subsequent commutators are also going to go to 0. That's another thing you can try out if you would like. I'm just going to tell you that that's the case because otherwise I'm going to be recording this video for even longer than I originally anticipated. Okay, so then let's put it all together, right? This is the first commutator. And so our PZW transformation on this first term, right? It's going to be P minus Z times A plus the result of this commutator. So let's copy this down here. And I'm going to write here, just so that we're clear, using the fact so using the fact that that commutator is equal to plus Z a hat, we can see that this transformation gives us, so I'm going to write it a few ways just to be clear. First, I'm going to write it equal to P hat minus Z a hat, that's the first term, plus Z a hat, which is the same thing as P hat. All right. So now, right, are we done with that first term? Not quite, right? We're not quite done. So here's what we actually have to do, right? We have to remind ourselves that we actually wanted to transform the square of this operator. Okay. And what this gives us, because of what we've seen happens to P minus ZA, well, that is going to get rid, that is going to turn P minus ZA into P. So overall, this transformation on the square of that is going to take us from P minus ZA squared to P squared. Okay. And so then the result of this is I'm going to get 1 over 2m times P hat squared. So what this has basically done, and this is now done. Okay, we're done with term 1. Okay, we're done with term 1. And what has happened is we have taken now this kinetic energy term in the P dot A Hamiltonian that we started with, right? because this overall thing was a kinetic energy, right? P squared over 2m is kinetic energy. So we had this coupling to the photon in this kinetic energy like term, and we've just and so that kinetic energy piece was actually sort of a mixed photon matter piece, and this transformation has evidently removed the photon character from that piece. Now it is just a pure matter kinetic energy. All right. So that was the first transformation, and what I want to do now is I want to talk through what's going to happen for the remaining transformations. And we're going to actually, you may remember we have a take-home midterm coming up. So I'm going to leave the last transformation, the details for you to work out as an exercise, but we'll have the final result in lab anyway. So you'll have something to check against, but I'll let you work through the steps yourself. But let me make a few arguments here about term 2 and term 4, right? So term 2 just involves the matter position operator, which is going to commute with the matter position operator in the PZW transformation. So this term will be unaffected. And similarly, term 4 is just the photon position operator, and the PZW transformation has the photon position operator in it. And so those will commute with themselves, right? And so also this will not be affected. So what will be affected is term 3, which is the photon momentum operator squared. And so basically what's going to happen, right, is we have to figure out the magnitude of the shift, but we know that we're transforming with some magnitude, right? Basically the magnitude is something like mu hat times lambda naught. That's like the magnitude multiplying the position operator in the PZW transformation. So we should see something like lambda naught mu hat is related to the magnitude of this shift on the photon momentum operator here in term 3. So basically, if you go down the line and apply the PZW to term 1, term 2, term 3, and term 4, term 1 is going to have the matter momentum shifted by the amount ZA. Term 2 is going to be unaffected. Term 3 is going to have the photon momentum shifted by some amount. The precise amount you need to work out, but mu hat and lambda naught have to enter into the equation. And then term 4 is going to be unaffected. Okay. So anyway, that was the conclusion of our introduction to unitary transformations. I'll put these notes up on our Google Drive, and I hope to see you all on Wednesday.